Okay, class, this is lecture number 8 for your Exercise Science 122 Strength Training class. And this lecture is on plyometrics. So this is going to be the most in-depth lecture as far as anatomy and physiology that we go into. There's some important aspects of this lecture that you're going to really have to know as far as testing material, and I will point those out as we go. There's a couple of things that we have to define first anatomically for you to be able to understand the mechanisms in which plyometrics occur. So to have a base understanding of plyometrics, this is anything that utilizes what's called the stretch shortening cycle. It's a basically an anatomical and neurological strategy used by the body to basically produce more force quickly. So when we're talking about athletics and we're talking about sports and performance, a great deal of the actions that are done in order to yield successful sport movement are predicated on stretch shortening cycle movement. So things that are reactive. So if you use the word reactive, I think it's a little bit easier to understand at its core, but it's the difference between doing a jump where you sit there for, like, if I held you in a squat for 5 seconds and asked you to jump, compared to if I let you run up full court and try to touch a basketball rim. The difference in those two things are plyometrics and not plyometrics, because one is utilizing what's called a stretch. Okay, and the stretch is what aids in the ability of you to produce more force, you produce it quicker, and therefore you jump higher and you do these actions a little bit more explosively. Okay, so that's the basic understanding of what plyometrics are, but as part of this class and future classes, you will have to know the exact mechanisms in which this occurs. So before we do anything, we actually have to define some anatomical structures of the body for you to basically understand where we're even at. So what we need to go over first is what's called the series elastic component. Okay, it's just referred to as the SEC from now on. That is the workhorse of the plyo. Okay, so this is essentially where most of the energy you're going to gain from going through the stretch shortening cycle is going to come from. So if you go all the way down to the bottom of the page, you'll see what's called the mechanical model of skeletal muscle. And within that, there's 3 things there. You have your SEC, your series elastic component. And remember, that's the workhorse of the plyo. You have your parallel elastic component, your PEC. And that's the epimysium, perimysium, endomysium, and sarcolemma. Those are just the wrappings, essentially, or the layers of muscle. So the actual muscle belly, those are the things that essentially group together not only the different muscle fibers, but the individual muscle fascicles that are laid in between, all the way down to almost all the way down to its contractile parts, which, if we look, the contractile component. So the actual anatomical mechanism in which muscle contracts, that comes from basically actin, myosin, and what's called the cross bridges. So essentially, actin and myosin are 2 proteins that link and attach to each other. The myosin heads attach to actin and pull the actin, right, which basically closes it pulls the different muscles together. This is called the sliding filament theory. We are not going to go into that. That is something that you will get an introduction to in Exphys 1, I'm pretty sure, and as well as strength and conditioning theory. So that's a concept you have to understand, that basically the where and how muscles contract, it's basically because of 2 types of filaments, thick and thin, interacting with each other and sliding closer together or past each other based upon those different aspects, the actin and myosin closing it together. Okay. Now, the thing about plyos is the contractile components the actin and myosin and the cross bridges aren't going to play a main role, but they are part of it, and that's on the neurological side, and we'll get to that. So if we look up to the series elastic components, we'll see that there's the tendon and the cross bridge. So if you look at any muscle, right, you have the muscle belly, right, and if all of us think about it, a bicep muscle, right, we can all identify where that muscle belly is. Well, all muscles have attachments. So the muscle doesn't attach right to bone. There's something in between that attaches the muscle to the bone, and that's the tendon, right? This tendon is like a very fibrous material that's elastic, that gets the bone connected to the muscle. Now that tendon runs basically from the bone on one end So from the bone on one end, it'll run in and turn into the muscle belly, but part of it will run directly through the middle, and then it will come out as a tendon on the other side. So that's where you get this tendon and cross bridge connection, is in the middle. It's called the aponeurosis, and that's where you have the interaction of these two things. So the SEC basically is the thing that elastically gets the muscle together. Now, when I say elastic, I want you to keep in mind or think about like a rubber band. Okay, so what happens when you stretch a rubber band, right? It's elastic, so it's something that if you stretch, it'll return to its original form, and it does it very quickly because when you're pulling and stretching that band back, you're creating energy. And when you create that energy, it's going to fire back. So that's where this whole like stretch shortening cycle, energy production, added force, velocity comes from. We're going to get into it a little bit more depth, but just understand that that is the workhorse. That is the anatomical thing. That is where most of this is going to come from, okay? So if you go back up to the top of the page, there's three things that we have to define. The first one is what's called potentiation. Now, I'm going to read the definition, right? A change in the force velocity characteristics of the muscle's contractile components caused by a stretch. All that means is if you get a stretch, you're going to change essentially the immediate capability of what that muscle is going to be able to do on a force aspect and a velocity. So think of like strength and speed. Okay, so essentially, the faster I stretch something and the further that I stretch it will allow me to produce more energy depending on not just the magnitude, but also the rate. Okay, so and depending on where that is, you're potentiated. You have more potential to create energy from that standpoint. So that is what's going to change this force velocity characteristic. We're not going to get into the force velocity curve. I will say, if we look, pretend on this wall, okay, on here, on the y-axis, pretend that you have force, okay, and on the x-axis, pretend that you have velocity. Velocity is measured in meters per second, and then force is measured in newtons, right? So if we look, if we're on if we're going to look at the most force that someone can produce, that is going to occur at 0 speed, right? So you wouldn't be able to move if you're producing the most force possible, okay? So that's at 0 speed. As I am increasing speed, I consequently have to decrease force, right? So the curve will slowly start to go like this, right? So the more speed I produce, the less force I produce. The more force I produce, the less speed I produce. It's essentially an inverse relationship. So having that understanding will allow you to understand basically what the force velocity characteristics are and then how you can manipulate those through a stretch. Now, the stretch reflex, okay? I'm sure some of you have heard this term, but what that does is it's going to increase agonist muscle activity. We'll get into that. It's the body's involuntary response to an external stimulus that stretches the muscles. This component is primarily composed of muscle spindles. So, at the beginning of the lecture, I told you that there's an anatomical and mechanical side to the plyo, and there's also a neurological side to the plyo. This mechanical one we already went over, and that is the tendon and the SEC, which is the tendon and the cross bridges. That's the mechanical side, right? On the neurological side, your body basically has some checks and balances in it to ensure that it doesn't get hurt. So that's what a muscle spindle is there for. It's essentially something that is going to increase what's called the agonist muscle. So the agonist muscle is the one that's being used, right? So think about it that way. So if I stretch my arm like this, super, super fast, what I need to do as this bicep muscle stretching is that my body is going to it needs something to sense that, whoa, I'm stretching way too fast and with way too much force. And if I continue to do this, my muscle is going to rupture. So the muscle spindles, they sit within the muscle belly, and what they do is they sense the magnitude and the rate of a stretch that's occurring. If it senses that this stretch is too fast, too strong, or both, what it does is it makes this muscle contract concentrically, right? So remember, we have eccentric movement, which is the stretch of a muscle. So when we get something stretching, you got to think it's going eccentrically. The agonist muscle activity turns on concentrically to combat the eccentric stretch. So On top of having our SEC, which is the workhorse, and we'll get into this in a second, you have something in there which is a protective mechanism, which is the muscle spindle. It's called a proprioceptive organ. So all that means is it's aware. It's basically measuring or taking into account what external stimuli are getting put on the body to ensure that the body maintains at homeostasis. So for a muscle to stay at homeostasis, what it needs to do is move within a range that is safe to allow the muscle not to rupture or strain or get injured. So these muscle spindles are in there to sense that stretch or that magnitude and the rate of the stretch in order to protect the muscle. What actually also ends up happening is that when you get a stretch and that muscle contracts, it's going to help add a force component to the other side of that movement, right? And this is where that stretch shortening cycle comes in, and this is where plyometrics come in, is once you get the blend of the SEC of stretching elastically to create energy, on top of you get that muscle to contract the opposite direction, the reactive direction. Now you get a muscle contraction on top of the elastic energy that was created from the stretch in the first place, yielding you to be able to have a more forceful and a higher velocity movement. Okay? So what happens is that the SEC, when it's stretched, it's going to utilize energy. It's going to get that energy when it stretches fast enough, and you're going to get energy from that. Okay, because of the stretch and the nature of what the tendon can do. Okay, so the thing about plyos is that all this is assuming it happens within a specific coupling time, and coupling times just means for the whole action to occur. So what we're looking for is a very short coupling time. So plyometrics have a little asterisk on it because the defined time for a plyometric to occur is 0.25 seconds or less. So if you can't complete the action in that time frame or less, you are not fully utilizing the stretch shortening cycle. Okay? Now, we're going to get into the specifics of the mechanical and the neurological side of in the phases of action of a plyometric. Okay? Now, what I want you to do, if you see there's a table here, okay, we're going to leave this table here for a second, and we're going to go to one that I created, and I'm going to walk you through step by step how to go through this table. So what I need you to do right now, and you pause the video if you need to fill this out, what you're going to do on the left columns is you're going to write eccentric in the first column, amortization in the second column, and then concentric in the third column. In the rows. I apologize, in the rows. Then when you get to the columns, you're going to have SEC parentheses mechanical in the first column, and then you'll have muscle spindle parentheses neural in the second column. Okay, so go ahead and fill that out. Pause the video if you need to so that you can follow along. Once you've completed that, in the SEC mechanical column, next to eccentric, you are going to write rapid stretch deforms the SEC. I'll say it again. Rapid stretch deforms the SEC. Then, in the amortization row, in the mechanical column, energy is stored in the SEC. Again, energy is stored in the SEC. Lastly, in the concentric row of the SEC mechanical column, elastic energy is released during the subsequent contraction. Go ahead and write that down. Elastic energy is released during the subsequent contraction. Now, in the muscle spindle, the neural column of the eccentric row, you're going to write senses the magnitude and the rate of the stretch of the agonist muscle. I will say it again. Senses the magnitude and the rate of the stretch of the agonist muscle. Next, in the amortization, sends signal to the central nervous system to tell agonist to contract. Again, sends signal to the central nervous system to tell the agonist to contract. Lastly, in the concentric row of the muscle spindle column, agonist receives the signal and contracts. One more time, agonist receives the signal and contracts. So, pause it again if you need to fill anything else in, but you have to have this table filled out to follow along. So when we're talking about a plyometric, right, we have already gone over that we have a mechanical side of things, which is the EXSC, the elastic part that stores energy, and we have also gone over what's the neural side, which is that muscle spindle, the proprioceptive organ that is there as a protective mechanism against stretch, eccentric stretch, right? So real quickly, if we remember, when we're talking about muscular contractions, we have our three phases. We have our concentric, our isometric, and our eccentric phases. When you are talking about plyometrics, they are not the same. You still have a similarity in the eccentric phase. You then move to what's called an amortization phase. The amortization phase is different from the isometric phase because in an isometric muscle contraction, all you are doing is matching the force in order for you to stay at that spot. The muscle is not moving at all through any ranges of motion. It's not changing its position. It is just matching the force of what's placed upon it. With the amortization phase, you are literally waiting for that muscle spindle and that signal to go back to the CNS, right? So you have an actual task at hand, a secondary task at hand that has to occur. So you have to understand that difference. What you are looking for with plyometrics is quick amortization phases. That's that coupling time. If the coupling time takes too long, you have ruined the plyometric, and we will get into that. So, to go over the chart really quickly, what we know is we have our mechanical model, and we're talking about the SEC. The first thing that happens is the eccentric part. There's a rapid stretch which deforms the SEC, right? That's our rubber band. We take our rubber band and we go stretch, right? So all we've done is stretch the band at this point. When we go to that amortization phase, the energy that you created when you stretch the band fast now is stored. It's staying there. If the coupling time is fast enough, if you get through this process quick enough, you get to the concentric part. And in the concentric part, that elastic energy you created is released once the next contraction happens, which is the rebound. So once you get to the rebound, you get that release of energy, and that extra energy is going to help you produce more force, produce more velocity in the subsequent movement. That is the mechanical model of what happens. When we're talking about the neural side, that's the muscle spindles and the proprioceptive organs. So if we go to the eccentric part, those muscle spindles, the first thing they do is they sense the magnitude and the rate of the stretch of that agonist muscle, right? So if we look at the muscle, right, they're sensing, oh, we're getting a stretch that's way too fast and way too hard. Okay, so what do we have to do? In the amortization phase, as we're getting through that stretch, that signal is then going to be sent from the muscle spindle to the CNS, and we're telling the CNS to tell the agonist muscle that, yo, you got to contract, right? You can't keep stretching to combat that stretch. So when we get to that concentric part, this is when that signal has made its way back to that agonist muscle, and it knows, oh, I got to stop stretching, I have to start contracting. Now, that right there is all given, right? All of this is a given that you have a plyometric and all these things should occur, assuming that coupling time is quick enough. So if you're not doing these actions quick enough, you're losing out on not only the effect of the muscle spindle, but you're going to lose the energy that was stored in the SEC as heat. Okay, so the last thing that you want to do is do something too slow so that you're not going to be able to reap the benefits of the energy that you created. So if we look at it, if you're trying to jump with heavy weights, okay, and I go through a jump and it takes me too long to get off the ground, I have just turned that explosive plyometric action into something that's not, because I am not actually following the guidelines to give this mechanical and neurological model. It's not fitting the time frame that it has to be in order to actually utilize the benefits. So, for example, if I'm going to have somebody do jumps in place and I want them to have some weight, some overload, that's okay as long as they are matching the coupling time. So as long as each jump they are on the ground for less than 0.25 seconds, well then we know we're doing a good plyo. If not, then we know we're not. So that's a measuring tool for you to understand to make sure that this is happening. So if you're training somebody to be explosive, if you're training somebody to gain that ability to produce force quickly while utilizing the stretch shortening cycle, you have to make sure you're following the right guidelines, and now you know the exact mechanisms of why that is working or not working. So if we go back over here, the next three parts of this lecture: the storage release of elastic energy, the mechanical model, and the neurophysiological model. Those are essentially what we just explained in the table. Okay, I took those things and put them in the table because it's easier to understand. You can see them happening side by side. So, if we look at the storage and release of elastic energy, right? The first thing that happens is we get the rapid stretch that deforms the SEC. We already went over that. That's the eccentric phase. That elastic energy is then stored. Okay, it's stored with that deformation. The elastic energy is then released during the subsequent concentric contraction. So it's the rebound, the reflexive part of it. That's when you get the release, and that's assuming that the coupling time is short. What this allows someone to do is perform more work in less time, and that's what you're trying to accomplish. So plyometric actions you see all the time in team sports and athletics, because essentially you're trying to beat the person to the spot. If I can jump up quicker and utilize my stretch shortening cycle better compared to the guy next to me, I might have a better chance of getting the rebound or catching the pass or defending the pass. Whatever that task might be, plyometrics play a role. Now, we've already went over the mechanical model, but if we go to the next page and we look at the neurophysiological model, right, all we see is that the stretch reflex, right? It's the body's involuntary response to an external stimulus that stretches the muscles. Okay, so what we're looking at is the muscle spindle. It's that proprioceptive organ. Don't worry about what the intrafusal fibers mean for now. Just understand that these are sensitive to the rate and the magnitude of the changes in muscle length, of the stretch. Okay, and during that rapid stretch, the reflexive muscle activity increases in the agonist muscle, and this is an attempt to maintain the muscle at the original length. So again, this is a protective mechanism for the body to try to maintain its homeostasis. Everything that happens to your body is an attempt for it to go back to where it was because it senses that something is off. That is the nature of homeostasis, and when you train, you are constantly trying to pull the body away from the homeostatic level was before, and you're trying to make a new homeostatic level. So whenever you do any type of training or induce stress, your body is going to sense that, and then is going to try to build to prepare for that stress again. So the more consistency that you apply a stress to somebody with the right amount of overload and volume that is specific enough to the task, you will continue to raise that level of homeostasis to whatever level that they need. So understand, this is the physiological and anatomical